All right, we have the first submitted talk by Xinyi Wan on use of Coq in a logic class. Go ahead.
Okay, thank you for your introduction, and hello everyone. I'm very glad to give a talk about our usage of Coq in logic education, and it is a ZFC set theory prover that developed by me and my advisor Qinxiang Cao for discrete mathematics teaching. And we all know that the study of logic is essential to students of computer science. And when teaching logic, the very important thing is to make sure that students have understood inference rules, so that they can write the proofs correctly. And this job is typically done by teaching assistants. You know, they will check your homework, and they may find that you have write something wrong like this. But since nowadays we have powerful theorem provers like Coq, so why not just let Coq be the proof checker? And Coq can bring us very, very good things. And the first is that students just cannot prove these wrong propositions in Coq. And another great advantage is that the immediate feedback. Suppose that the teacher leaves assignment and you hand it over a week later, and it will take another 1 or 2 weeks for the TA to point out that you don't apply the inference rules correctly. But if students can write proofs in the Coq, so Coq will tell them that you don't apply this inference rule correctly at the moment. And another feature is the interactive feature of Coq is also very helpful because students can go up and down through the code and see the change of the proof state. And this will benefit their understanding of proof rules. But there is one question, that theorem provers like Coq are for professionals, or at least well-trained students who have carefully read software foundations. And for beginners, they are likely to confuse the meta logic and object logic that they are learning. And another obstacle is that the proofs in Coq are so different from those on the textbook. Let's take the associative law of intersection, for example. In the textbook, everything is concise, it's elegant. But when you want to formalize this law in the Coq, you may get something like this. And you have all sorts of type-classes things and a very long formulation. And for beginners, it's just scary. So if you wanted to introduce theorem provers into logical education, especially for beginners, then it is very important to narrow the gap between textbook and Coq proofs. Sorry. And in this case, we focus on the first-order logic and the ZFC set theory because these are standard parts of such courses, and we develop a mini ZFC prover embedded in Coq for teaching purpose, which hides the meta logic of Coq, and so that students can, when students reasoning in the provers, they are dealing with traditional terminologies and notations that is exactly the same as the textbook, and they can reason with few tactics we provided to help them prove the theorems more easily. And this prover is aimed for users have no requirements for users, so they don't need to have any knowledge about theorem proving or Coq before. And we believe it is easy enough to learn. And I will start with a very simple demo. Sorry. All right, and okay. Is this okay? All right. The prover adopts the natural deduction system, and here is a very simple lemma that we wanted to prove that for any sets U and V, their intersection is a subset of U. And let's begin the proof. So the first step is post-proof intersection if. Then we get a hypothesis about the intersection, and it says that for any set X and Y, then Z is the elements of each intersection if and only if Z is both their elements. And next, we can use the elimination rule of universal quantifiers. So we can instantiate the for X, for Y, for Z in H into U, V, and Z in H0. And the next step is a technique called total. It will do propositional reasoning, and you can easily see from the hypothesis that from H0 to H1 there will be only operations about logical connectives, and there won't be any operations about quantifiers. So this step can be directly solved by the total. And next we can use the introduction rule of universal quantifiers and take this for binaries back into the conclusion, and we get the hypothesis H2. And the H2 is exactly the same as the goal we wanted to prove, so we can use the conclusion is already proved tactic to finish all the proof. Yeah. And you can see that the whole proof pattern it follows a forward proving pattern, which is not a typical, which doesn't seem like a typical Coq proof. But this is exactly how a natural deduction system works on a textbook. What's going on here? All right. Okay, let's carry on. And now I'd like to talk about the design of the prover. It can be roughly divided into two parts. And the first is the formalization of the set theory, which students do not need to understand. It includes the Coq formalization of these terms, these deduction calculus. But you know that students don't need to bother that all these inductive definitions and these codes. And another thing that students do not need to understand is Coq itself, because we hide the meta logic of Coq, and so these inductive types, these L tags, etc., they are invisible to users. And for them, from their view, Coq just serves as a proof checker that only allows first order logic and the ZFC set theory. And of course, they do not need to know any tactics originally provided by Coq. And the second part is the proving environment where students interact with the prover. And what they do need to understand is the set theory and the first order logic on the textbook. Because our goal is to narrow the gap between the Coq proof and the textbook. So students must know what this rule is about to continue his reasoning. And if he decided to, for example, to apply this elimination rule of universal quantifier, then he should choose the corresponding tactics and in our prover. And so he needs to know the effects of our tactic. And we provide a tutorial Coq file so that students can learn the tactics by examples. And here is the formalization part of the set theory. We choose a deep embedded approach. Here is the terms, and we have the constant symbol that is empty set. We have the variables, and we take a nominal approach. So every variable has a name as a string. And we have these function symbols like singleton, intersection, and union. So the whole term is formalized in a first order style. And then we can have the propositions. The two atomic cases are the equality relation and the set membership. And we have all of these normal logical connectives and these two quantifiers. And now let's move on to the deduction system. We choose the natural deduction calculus, which is on the textbook. And it composes of a context, which is a sequence of propositions, and that derives one propositions on the right-hand side is the conclusion. And these rules are directly copied from the textbook. We have rules about connectives, we have rules about quantifiers, and we have these ZFC axioms. And this formalization of the set theory is nothing new, and I believe that all of you are familiar with. But what I want to emphasize is that this deep embedded approach gives us a very clear object logic, so that students can deal with the propositions they are familiar with. And here is the example of the axiom of extensionality. And this is the formalization of this code in Coq. And you may notice that these variables x, y, and z, they seem to come from nowhere, because as they are not universally quantified in the code. That is because our formalization, in our formalization, these variables are strings and they are predefined in Coq. So there is no need to universally quantify them in the code. And this is actually a good thing, because when students in the proving environment, they want to prove the axiom of extensionality, what they will get is the hypothesis H, and it is exactly the same as the textbook, and there will be no other side conditions. And here comes the crucial part, tactics, because the students rely on our tactics to interact with the prover. And the principle is that the tactics should reflect the inference rules, but we also provide some automation to help them prove these theorems more easily. And we suppose that our students are familiar with propositional logic, so we fully automated propositional reasoning in one tactic called T-auto. And this substitution and alpha equivalencies are also automatically calculated, and students do not need to concern about it. And there are 8 tactics that students need to understand to finish their proofs in the system. The first is a post-proof that is originally in Coq, and there is the second part is propositional reasoning tactics, and there are 2 of them. One is assert something by T-auto, and the other one is the conclusion is already proved. It is actually an alias of T-auto, so that students can use it to end the proof of a theorem. And there are also ad hoc tactics for quantifiers and the equality substitution rules. And this basically resembles the proof rules in the first order logic, but we also add some automation into it. And I will explain them later. And first, let's find out what T-auto can do. And here is the example. We have 4 hypotheses. Here, the hypothesis H means that X is an inductive set, and it derives that empty set belongs to X, and H0 is exactly the same thing. And in H2, we have a property about intersection with X and Y and the empty set. And now the user wants to assert this proposition, that is X and Y are inductive sets, and they will derive that the empty set belongs to the intersection of them. And we can see that from the hypothesis H0 and H2, we can derive this assertion and without any operations about quantifiers. So it will be accepted and directly added into the proof environment. So now let's see how the T-auto tactic actually works. Here we use another example, and there is two hypotheses, and H0 is that the set Y doesn't belong to the empty set, and now the user wants to assert that if Y it belongs to the empty set, that implies that Y belongs to X. And the first step is to combine all these hypotheses and the assertions into one first-order logic formula. And because we know that the validity of this formula may be undecidable, so we will transform it into a propositional language formula that we will try to solve it in the scope of propositional logic. And we will assign propositional variables to this quantified subformulas. For example, the first one is started with for y, so we assign a variable x to it. And for the atomic subformulas, we also assign a variable called y, and the same is about z. So we got a propositional logic formula is in this form, and you will notice that there is a negation in front of it. That is because validity is equivalent to the unsatisfiability. And then we will generate a conjunctive null form of it. And these two formulas will have the same satisfiability, and we will just throw this CNF into a DPL solver that we implemented in Coq. It is a quite simple algorithm, about 300 lines, so it doesn't produce any witnesses. So it just produce set or unset. And once it is produced unset, it means that this formula is valid and it will be added into the proof environment. Currently, this whole process is unverified, so it is guaranteed by an axiom. But we are actually verifying this, and we reckon that it is correct because we haven't met any problems in the verification by now. And here's those ad hoc tactics for the quantifiers rules, and this, for example, the universal instantiation. And here is the axiom of extensionality. And if the user wants to get the property of extensionality for two concrete sets, for example, the X and the empty set, then the universal instantiation will apply these rules twice, and we will get this extensionality about X and the empty set. And for the extensional quantifier, it has a different flavor. Here we still use a very trivial hypothesis, and what the user do is he will directly write down the proposition he wants. For example, here is exists U and V, that U belongs to V. And this tactic, it will search and it will compare the assertion and the hypothesis, and it will decide which terms are abstracted, and it will then compare that and check whether these two formulas are really equivalent. And there will some alpha equivalence things in this process, but it will automatically resolved by the tactic. And of course, in this case, it succeeds. And we have used these tools to teach set theory to undergraduate students in a discrete mathematics course. And these students are first-year students with no theorem proving experience. And we provide a course project that we ask them to prove the mathematical induction with this tool. And we do not provide much materials. There's only a tutorial Coq file with 300 lines and a 15-minute video that's introducing these concepts in the tutorial. And there are no other Coq teaching in the class. Yeah. And finally, we provide them with 3 goals that we want them to prove mathematical inductions step by step. At the beginning, we are not completely confident about this because we tell them so little about Coq. But actually, the result is quite encouraging. There are 2 optional course projects in this course, and 8 out of 15 students choose this, and all of them make it. The best student with no theorem proving experience spend an afternoon to solve this proof with 65 lines, and while the teaching assistants, well, me, cost 67 lines. And you may notice that some students' proofs are substantially longer than others. That's because they didn't make full use of the automated propositional reasoning. And since we still have some time, I want to demonstrate that how mathematical induction is proved. And here is a base step. What we want to prove is that the n is the set of natural numbers, and 0 belongs to x. And for every natural number, if it belongs to x, then its successor also belongs to x. And the base step is to prove that it is the 0 belongs to their intersection. And this is a quite straightforward proof. We just use the property of intersection and instantiate with the sets we want, and it's already proved. And for the inductive step, we show part of them that we want to prove that if y belongs to the intersection and its successor belongs to x. And still, we use the property of intersection, and we assert we wanted to use this condition in the context. So we first assert it that it derives itself, and then instantiate with the number y, and the other things are solved by the propositional reasoning. And the next lemma is exactly the same, so I will skip it. And for the inductive step, we just post-proof all these lemmas, and we'll prove the inductive step. And then with these two steps, we now have that the intersection of x and the natural number set n, the new set, it is also an inductive set. And finally, it is the mathematical induction. First, we post-proof that the lemma we have just proved, and then by the definition of natural number, we have that for any inductive set W, then n is subset. And by some instantiations, then we have that for any specific natural number n, then it must belong to the intersection of x and n. And finally, use the property of intersection, and we will get to the results that for any natural number n, it belongs to x. So let's finish the proofs of mathematical induction. Right. And here is a code distribution of our project. The formalization costs 6,000, not 6,000, 600, and the T-auto costs only 400 lines, and some may wonder that why we use so small lines of code. That is because that the DPLL is really a simple algorithm, and we haven't verified it, so it only costs this 400 lines. And we are currently verifying it, and we estimate that it will take 1,000 to 1,500 lines. And among all these 2,600 lines, the code that students need to understand are only the tutorial file with that 300 lines. And for future developments, there will be 3 directions. With the most feedback we get from the students is that they want more automation. For example, the set operations, they think that these propositions like this should be solved in one step, and even some students want those quantifiers and can also be automated, but this is too advanced topic for them. And there is another improvement is that we are looking for effective representations of numbers and arithmetic operations. We have actually already formalized the Peano arithmetic with addition and multiplication, but it is all under the framework of the ZFC set theory, so that it is not very decent, and we just ignore and don't want to show it here. And the third Third direction is graphics interface and proofs. There are some very excellent works about graphic tools that use to teach logics, but they are not in theorem provers because that will be a very hard topic. But I noticed that today in a talk later today, and there will be a talk about the graphic proofs of formal proofs, and I'm very looking forward to it. And our prover has been available on GitHub, and thank you. That's it, and I'm happy to answer your questions.
Hi, thanks for the very nice talk. So actually, I'm Pablo Donato. I'm going to do the talk about the graphical interfaces in Coq. But so yeah, I'm really interested in what you're doing. I had just one question about your Toto tactic. So is there any reason why you don't use the one from the classical module in Coq and you re-implement it from scratch?
That is because our formalization of the set theory is just from scratch. So it is a quite complicated process, and it's not can be resolved by the Toto tactic in Coq. So we have to implement such a program in scratch. Yeah.
So I guess when I learned how to program in Coq, I did it with the Software Foundations textbook, and they take the approach of kind of starting off without teaching you tactics and then only teaching you the automation after you've like been doing it manually. I guess I'm wondering if you had any students who were writing the conclusion is already solved without actually understanding why it's solved.
Yeah, we have emphasized that this conclusion is already proved, only is available for propositional reasonings. But yes, there are students that try each step with this conclusion is already proved. And I think that this is a common phenomenon in using Coq in education, because students turns out to try all possible tactics to proceed and to solve this problem. Yeah, it doesn't. I can't think of a very good solution for it.
You had a question earlier.
So I don't remember how you said that like you had this deep embedding of ZFC in Coq. So are there any issues with the fact that Coq is constructive and like their students are reasoning classically?
Yeah, students. This formalization is only about the proof rules. So students just check the students whether students applies the proof rules correctly. So it will have the problem that you have mentioned, but for a small demo that's only teaching beginners, then it will be no problems.
Hello. So far, you have only showed us the positive examples where the tactics actually go through. So can you show us a negative example? Like what happens if the student tries to solve a thing with the conclusion has been proven that cannot be proven by the tactics?
Yeah, there's a very simple one. I will.
Can you just add that line to the middle of some proof?
try to just create one.
The answer just nothing.
Yeah, I think the question is really with the error messages.
So I did prepare a negative example, so I try to.
Presumably, if you stick this at the beginning of the proof, it won't work, right?
Or you want to see what's going? Oh, all right. There will be just a error message. It's just a liability auto, so I will just use it. Yeah. Yeah.
You showed a brief evaluation section with 8 students who all made it, which is great. And I understand that this is the first time you're trying this. But do you have any more detailed, maybe even like anecdotal anecdotes from the students about what they found was an improvement using this, or how they compared to students who did not did not learn the same stuff using Coq? Or what are the additional pain points that this introduced for students versus learning it the more traditional way?
Yeah, for there there is some pain points to use this, because there are some obvious conclusions that for students who doesn't use these tools, they will directly write on the paper and in one step and say this is right, and for teaching assistants, and they will acknowledge that they are indeed right. But if someone is using these tools and he tries the same thing, and it will fail. So yeah, indeed, the usage of Coq will bring some pain points, but I think that the students who have tried these tools, and they will have a more clear image about the proof rules, because with these steps, and they can see the change of the new derivations of these propositions. So and I believe that students who have used these tools will have a clearer understanding of the proof rules. Yeah.
All right, unfortunately, we're out of time for questions, but we do have a break coming up, and I'm sure you can talk to Xinyi and he'll answer your questions in the break.